Good morning and good afternoon, everyone, and welcome to our VCR Technology webinar. My name is Trianne Hupshali, and I am the Senior Brand and Marketing Manager here at WinGD. Just a couple of house rules before we start. Your microphones are automatically on mute so as not to interrupt the presenters during the webinar. If you have a question, to the right of your screen, you'll see a chat box. Please write your questions in that chat box, and our experts will answer them in the Q&A session at the end of the webinar. So here to present to you today is WinGD's General Manager Application Engineering, Marcel Ott. Our General Manager Product Management, George Limberopoulos, will also join at the end to help answer your questions. So please do write them in the chat box if you have any questions. So you can say hi, guys.
Hi, everyone. Good day. Good afternoon.
For those who want a copy of the slides, the presentation slides, you should be able to start downloading them right now. They should be available. Just before I leave, I just want to let everybody know that in case we don't have time to answer your questions, or in case you'd like to come by and say hello, we'll be at North Shipping this year in early June. So our stand is D02-23. So please come by and say hello. And we're also hosting a Meet the Experts on the Wednesday at 3 p.m. So please come by to that and say hello as well. And with that, I'm going to hand you over to Marcel. Thank you, everyone.
Thank you, Trianne, for the short introduction, and welcome everyone also from my side. Apologies for that little glitch before. Let's see if I manage to stay on stage here. We are very happy and excited to talk to you about our latest technology step for XDF LNG dual fuel engines, which is the VCR technology, as we call it. VCR stands for Variable Compression Ratio, and that is a new feature that we are introducing now that brings performance and emissions of our well-proven XDF engines to the next level. So we're very excited about this introduction, and you'll see some more details of this technology throughout the presentation that is coming now. So first of all, before we go into technical details, a couple of points on the current status of the implementation of this technology. In fact, this system, the VCR system, has been developed together with our Japanese engine builder, MESDU, which is formerly known as Diesel United, at that time part of IHI Group. And we also would like to thank IHI-DU for their great contribution they have done to this achievement. The system was tested on a full-scale 6-cylinder 72-bore test engine that is installed at DU's facilities and is available for testing purposes. And we have thoroughly tested this equipment and achieved very good results. We do have two first commercial projects coming with 62-bore engines for different ship types, as you can see here. And we have decided to now introduce VCR as a selectable option to the three engine types that are shown here: the X62 DF 2.1, the long stroke version of the 62 bore, then the 62 DFS 2.0, which is the short stroke version of the 62 bore, and then the 72 DF versions that you see here, which are the typical engines for LNG carriers that are also let's say sold in large numbers, and that is obviously one of our key target markets. We are at this moment intensively talking to engine builders, shipyards, ship designers to introduce this technology to them and to make sure that they can provide reasonable quotes on this technology. So first of all, what is the compression ratio for maybe some of you that may not be dealing with the combustion engines every day? Compression ratio is the ratio of the two volumes that are shown on the picture to the right. So the swept and the compression volume versus the compression volume that is left, the orange volume that is left across on top of the piston at top dead center. So generally speaking, the engine efficiency increases with an increased compression ratio, which means the fuel consumption obviously becomes better if the compression ratio is increased. What we have seen now on premix gas engines in general, and that is a rather, let's say, fundamental behavior of these engines, is that the compression ratio has to be limited to a certain maximum in order to be able to run under most challenging conditions, as we call them here. So full engine load, hot ambient conditions, poor gas quality, for example. But this also means that there is a bit of a compromise in, for example, diesel mode, where the efficiency is somewhat reduced if the compression ratio has to be limited to a lower level than what you would typically have on a diesel engine. And with the system that we're introducing now, the compression ratio can be set fully flexibly and variably at any given time to reach the best possible performance in both diesel and in gas mode. So it really enhances the flexibility of operation. Back to this old graph that we have been using for a while, and some of you might have seen before. It shows some of the fundamentals or characteristics of lean burn premixed combustion and its limits. So the graph shows a BMEP or torque on the left axis and lambda or air fuel ratio on the bottom axis. And you can see there is the green line, which is the operating line that is going up as the engine load or power increases. And then we have these two areas. First of all, the self-ignition high combustion speed area, which is the rich area to the left, this orange corner. So this rich limit we should not cross during operation. On the other hand, we should not go too far to the right, which then characterizes the lean limit, as combustion will become unstable and the emissions will deteriorate. So what we end up with is the green arrows that you see from left to right, which we call the operating window. And as you can see, as the operating window is relatively narrow at high loads or high torque, it becomes much wider going towards part load operation. And that is actually the feature that we're trying to utilize with VCR, because we do see a much bigger operating window in part load operation. We can also utilize that when running on gas to increase the compression ratio and improve fuel consumption as a result. Now, this is an example here of how the system actually works. And if we look at the graph on the bottom left, you can see compression ratio versus engine load of a typical engine. So in blue is the blue line indicates an engine that has no VCR and a mechanically fixed compression ratio. And as it's shown here, the compression ratio would remain constant in diesel and gas mode alike, as it is mechanically fixed and it cannot change. What we can do now with the VCR is shown in the with the green lines. So you can see that as the engine goes from full load to part load operation, the green line VCR gas mode starts to increase. So the compression ratio can increase as the engine goes into part load operation up to a maximum compression ratio that is set at low loads. In diesel mode, though, the compression ratio can be kept constantly at a high level, which is similar to the level of a conventional diesel engine. And that also allows to recover diesel fuel consumption to a similar level as on a diesel engine. The effect in gas mode is also shown to the right. Then you see the again a chart of efficiency versus compression ratio, and you see that as the compression ratio increases, the efficiency increases, and accordingly the fuel consumption is reduced, as you can see in the graph on the top right. In this graph we show in blue an engine without VCR, so a standard engine as we have it up to today, and the gray line shows the improved consumption in part and low load together with VCR. And as we look at typical operating profiles of engines in the field, we believe that this kind of shape with a reduction of consumption in part load specifically is actually very beneficial for the actual operation of the vessels. So how is the compression ratio being changed? And in fact, what it is at the end is that we can, with this mechanism that we have designed, we can change the position of the piston at top dead center. So as you see in the picture to the right, there is different positions of the piston in top dead center, and the piston position can be fully variably adjusted to any position in between that minimum and maximum. And as this compression or the position changes, the compression volume changes, and therefore the compression ratio changes. Just for comparison reasons, we have listed here a number of typical compression ratios of different engine types. You can see, for example, a diesel engine has typically a compression ratio in the range of 20 to 25, which is mechanically fixed by shims, so it's constant, it does not change. On a typical XDF 1.0 or 2.0 engine, the compression ratio ranges from around 12 to 16, depending on engine type, selected rating, and so on. But that is obviously the same in gas and diesel mode. On an engine with VCR now, we aim, of course, at having the, let's say, highest possible compression ratio at given operating conditions, which means in diesel mode, we can recover the same compression ratio as a diesel engine, 20 to 25, and in gas mode, we can also go up to as much as high as the engine operation allows. So how is this being done? And that's in a way the engineering core of the system that is shown here. We have let's say a modification to the crosshead design, and in fact what we have here now is a hydraulic mechanism that is fitted into the crosshead pin that allows to variably change the position of the piston rod versus the crosshead, and by that change the position of the piston top, as you can see on the left picture. Well, you can see from the left there is a kind of an oil feed system and a control valve, so a solenoid controlled proportional valve that controls the oil flow that is going through a knee lever into the crosshead and into the lower chamber of the lower hydraulic chamber of this mechanism. And the amount of oil that is fed here defines the position of this hydraulic piston in the crosshead itself. The design is very simple, very sturdy at the end of the day. There is a lot of similarities with other hydraulic system designs that we have on our engines, such as exhaust valve drives and so on. And the system is designed in a way as that we foresee no specific maintenance between dry dock periods of 5 years. So it's really quite simple and quite sturdy, straightforward design. There are a couple of subsystems to this hydraulic mechanism. First of all, we have this oil feed system that allows oil to be supplied to each individual unit. And you can see that starting from the left, the engine oil supply, the general bearing oil supply of 4 to 5 bar is used to, let's say, supply oil to this variable speed pump that is installed on the engine. The pump is relatively small. You can see 15 kilowatt that's an example of a 72 DF. 15 kilowatt is the nominal power, the maximum power, but in normal operation, the power consumption is less than 5 kilowatt, so it's actually negligible. The pump then feeds oil to this distributor rail, this manifold, and from there into each individual crosshead at relatively low pressure, 40 to 50 bar. That's enough. So that also is a reason why the power consumption is actually very low. You see here a very simple feed and supply system again. Another subsystem is the controls. So how the position of the piston is controlled. And first of all, this is all arranged by the standard WISE engine control system that is does not need any hardware modifications or module extension or anything. It's simply an update of the control system software that is required. And then the position of each piston is actually closed loop controlled. So there is a position feedback sensor on every cylinder liner that measures the position of the piston in every revolution. And the solenoid control valve then adjusts the position of the piston individually so that it matches the set point. Regarding operation of the engines and available operating modes, we do offer a number of operating modes to these engines, but actually compared to a standard XDF 2.0 engine without VCR, the modes are very much comparable. You can see we have the first 3 modes, this gas mode, diesel mode tier 2 and diesel mode tier 3, where VCR is active and fuel consumption is fully optimized to the best possible level. So that's the kind of standard operating modes, if we want to call them like that. Then we have this CSM or combustion stability mode, which is a standard mode or a fallback mode on every XDF 2.0 engine. And this mode allows the engine to run, to burn gas, even if ICER or VCR is not working for some reason. So what it will do is that you see both VCR and ICER is off, and it will work with a somewhat increased injection of diesel fuel in order to ensure stable combustion and still operate on gas, even if these two features are not available. So that's the gas fallback in a way. And then there is an optional fuel sharing mode, which is contracted sometimes for LNG carriers, not always, but is available to be selected optionally. And now the last one that you see here is the only additional mode that we have with the VCR system, which we call VCR fallback diesel mode. That mode is intended to be used in case of an unexpected failure of the VCR system. And that means the engine can go back to diesel mode operation, even if there is a failure of the systems here, and it can ensure availability of propulsion. So even if there is a failure, there is no any compromise in the availability of the engine as a prime mover. The only compromise is on the efficiency optimization, that it will not run fully efficiency optimized. But as such, we believe that's a simple and straightforward setup on how to do it. So coming to the actual performance improvement with this feature, and that's really where this feature makes a difference. As I mentioned before, we have seen significant performance improvements. In gas mode, we see a reduction of fuel consumption or gas consumption at part load and low load particularly. You can see this top right graph showing reductions of 2 to 6 grams per kilowatt hour, depending on engine load. So quite something. In diesel mode, as we saw before, we can keep the compression ratio at the highest level throughout the load range. So we also see that we have a kind of a BSFC reduction that is relatively constant over the entire load range, and this is rather big, with some 8 to 12 grams per kilowatt hour, depending on the engine type, engine rating, and so on. So that brings the diesel consumption to a very similar level as of a conventional diesel engine, and that also means that the, let's say, traditional compromise in diesel efficiency of a lean burn premixed engine has become void or has become obsolete. So that is not the case anymore. We can now provide highest possible efficiencies in both operating modes without a compromise. We have now used this kind of emission figures to calculate advantages and yearly savings of consumption, greenhouse gas, and finally OPEX of different ship types. And what we've done here is that we have used the consumptions as predicted or as shown on the previous page, and we have assumed typical yearly operating profiles of ship types that you see listed here on the left. Starting with this 174,000 cube LNG carrier, which is like a typical LNGC vessel with a twin 5X72DF 2.2 VCR. You can see the engine rating here. Then if it comes to the consumption savings or the savings overall, we have differentiated between GM, that stands for gas mode, and DM, which is diesel mode. So these are hypothetical assumptions or scenarios, assuming that the engine would actually run in gas mode or in diesel mode for the full time of the full year, which is of course not what they do, but this is a case simply to show the potential of the technology and to show what it can do. And you see here that the savings in diesel mode are actually the greatest, with some 5 to 7% savings throughout the year. So consumption savings, you see in gas mode 2.5 to 3% in that range for these different ship types. Greenhouse gas reduction is similar because that simply goes in line with the reduced fuel consumption. And if we then put kind of a price tag on the consumption and calculate the yearly OPEX savings, as you see on the column to the very right, you can see that this goes from around $300,000 per year of an LNG carrier to $550,000 if we were to operate on liquid fuels throughout the year, which it doesn't do, obviously, but you can see that in these scenarios the savings are quite significant. It's to be said that these savings, they are only based on, as they're calculated now, they're only based on the fuel savings, and there is no kind of reduction in any greenhouse tax that is to be expected in the future included in these calculations. With these kind of savings, we expect very short payback periods of this equipment and the additional costs that it brings of, say, a couple of years or so. A few words on installation aspects, a little bit more shipyard or ship design related. And I think that is one of the biggest advantages of this technology as such, because as you saw before, the technology is fully limited to installation on the engine itself. It does not have any impact on shipyard connections, on the main dimensions of the engine, seating, and so on. All remains unchanged. So the installation on board of a vessel actually is not affected by VCR as such. Same goes with the ancillary system. There is no change to the ancillary system specifications, such as pump and cooler capacities remain the same, and no additional pipe connections are required. So a very simple, let's say, it's very simple for ship designers and yards to implement this design in their ship designs. As there is no impact on the installation dimensions. What has to be done that I would like to mention here is same as for any new building project or new design, the torsional vibration calculation has to be done, so that the TVCs have to be reviewed. In fact, there is a difference, obviously, of the cylinder pressure curves on a VCR engine compared to a non-VCR, which means that the calculation of the shafting layout and everything needs to be done with the correct excitations to make sure the TVC is fine. But that's same as for any other new design and new project. A few words on the introduction schedule. First of all, I would like to repeat again that we are now focusing our efforts on the introduction of this technology on these three engines shown here, the 72DF, the 62 long stroke, and 62 short stroke. So that's the three engines where this will come as a selectable option. So it means you will have to select it as an option with the yard and the engine builder. We are considering then a portfolio rollout to widen the application of this technology to other engines in portfolio, but that will come as a second step and depend on actual market demands and priorities that we see. Further, we also now prioritize new building projects, but we do see a lot of interest for retrofit solutions. So to bring this technology on existing installations, and again, coming back to the installation related aspects, I think that is perfectly well possible, because as we saw, let's say all the features actually fit inside the engine room. There is no need to modify anything on the ship side. So a perfect fit for a retrofit case. Yeah, then you can see in the table some of the main documentation or documents and the availabilities that we foresee. We can provide preliminary performance data for these engines by now. GTD, so the full set of performance data is expected in July for the 72DF, including all the ancillary data and everything. And then you see the dates for complete set of drawing availability. So that's actually the last drawings. For those who know our systems, it's what we call the C drawings, so the last batch of drawings, which is early next year for the 72DF. And that means that we still expect a possibility to have a first engine delivery of a 72DF, for example, within second half of 2024. Now this is an indication from our side with the timing of engine delivery, and it has to be, of course, confirmed with the specific engine makers. But that is what we foresee should be possible. So with this, we're coming to a summary, last slide here. Again, with this VCR technology, I think it's fair to state that we can bring LNG dual fuel engines and technology to a next level in terms of performance and emissions. And that is also where the technology does provide additional value. Again, as we saw before, reduced gas consumption in part load operation, lower diesel consumption across the whole load range, and actually elimination of any disadvantage that we had before with this technology. Then reduced greenhouse gas emissions, as this comes along with the reduced fuel consumption, and that is something that every operator will be concerned with in the future. And additionally, we see that this system can provide extra flexibility for different operating cases. For example, extreme ambient conditions, for example, as a useful tool to extend the operating range with the PTO, because the engine can flexibly adjust its compression ratio and optimize the performance accordingly. So all of these points will bring a significant advantage and value to the end user of these products, and we're very happy to have it available on a commercial basis now. Yeah, so this actually brings me to the end of the presentation, and as Trian announced before, George and I are very happy to take any questions that you may have.
Thank you, Marcel. So we have
Managed to stay online at least. Huh?
We have a number of questions. Let's see if we can get through all of them. So the
Very
first
good.
question is, when is the first main engine with VCR will be delivered, and what kind of main engine that is? Well, we have the first engine we actually have right now. It's a 62 X62DF 2.1 engine that we have set for delivery, but that is on order. However, there might be a 72DF 2.1 engine that will be delivered before that. So it depends on the schedules and the slots at the shipyards. So, but those, as Marcel showed, those will be the bore sizes what we will concentrate. Another question is, which engine builder can install this VCR technology now? Once we release the technology and the drawings become available, any engine builder will be able to install the technology. A further question is flexibility for methane number or fuel gas supply pressure. As this is as we currently have today on the DF engine, so nothing changes. We minimum methane number remains the same. Fuel gas supply pressure remains the same. does not increase or reduce the flexibility. We have another question about the fuel consumption increase for the hydraulic power of VCR. So is there any fuel consumption increase for the hydraulic power? So we use, of course, we have a feed pump, but everything's on the engine. So we use the system oil and servo oil that we have from the engine. So that is all, let's say, included in the total consumption. We actually, because of the flexibility that VCR allows us, we actually have an overall decrease in both in diesel and gas consumption. Further question? Yeah, please add, Marcel. Yes.
Maybe one comment to that. As you saw, the consumption of the hydraulic pump during normal operation is something like 5 or below 5 kilowatt of power. On an engine with up to 16,000 kilowatt, this obviously becomes negligible. So I think you can say there is hardly any increased consumption due to the hydraulic power of the pump.
Thank you, Marcel. We have another question of how did we decide the compression ratio, the hydraulic amount? Well, okay, so the minimum compression ratio was chosen, of course, based on the compression ratio that gives us the optimal combination of the best performance and at the same time to ensure combustion stability. So that we knew, of course, from the tests we've done on the ICER engines. So from there, once we decided a safe minimum compression ratio where the engine can run stable without any issues with combustion, of course, at the highest load possible, from there on, then we could also make a range of the compression ratio. We can have minimum and maximum. So minimum at the higher, of course, loads, and the max we can increase the compression ratio at the lower loads. Then another question is ICER. We received a question if ICER will not be needed for fuel consumption improvement. Actually, the VCR right now, as we introduce it, will be on engines with ICER. So the combination of both brings us, of course, the best benefits. ICER has a function of increasing compression ratio, but VCR can take this function. Correct. Actually, VCR, the function of VCR allows us to actually go to even higher compression ratio at lower loads, which we cannot do today with ICER, because ICER has a fixed compression ratio, albeit a higher compression ratio, which allows a better engine performance. However, with VCR, we have increased flexibility. So we can go to higher compression ratios and therefore better efficiencies when running the engine at the lower loads. Another question, is it possible to retrofit the VCR technology to existing vessels that have an XDF engine? Yes, this is technically possible. However, this is not yet available, but it will be made available. WindGD is looking into a retrofit solution, a retrofit availability in the midterm. And Marcel, maybe next question, good question also, how VCR system will be worked in case of hydraulic pump failure?
Mm-hmm. Yeah, that is actually one of the fallback modes that we have seen before. So if the pump fails, or if let's say any failure of the supplying system or any other systems does not allow to operate the VCR system, the piston position will go to the lower mechanical end stop. So the compression ratio will reduce, and the engine will can be operated in either CSM mode as a gas fallback, or in diesel mode, diesel fallback mode. So the engine can still be operated without compromise in availability, but the fuel consumption rate, of course, in that case is not optimized.
Thank you, Marcel. Also, the next one, maybe we can revert to one of the slides. It's about the NOx technical file. How can the NOx technical file be described? So the highest compression ratio case and VCR off condition. How will that be? I think we have a very good
Maybe I
slide
can
on that we
go
minimize
back
the effort.
to that one. You can see the NOx compliance of different modes. So gas mode is with VCR on is tier 3 compliant as a standard operating mode. Then diesel modes are tier 2 or tier 3 depending on the mode that is selected. And these modes have to be emission certified and described in the NOx technical file.
Thank you. And stay on the slide. The next question is, what is the meaning of if contracted optional in case of diesel tier 3 mode, as we show here on line 3? It's
Yeah.
pretty
Actually, that is referring to the fact that a normal standard ICER engine doesn't necessarily have to come with a diesel tier 3 capability. It can be, but so far it's also as a selectable option, available as a selectable option.
Thank you.
And same with fuel sharing. So it is available for selection if needed.
Then one of the next questions as well, similar, is CSM. So is the combustion stability mode regarded as a gas fallback mode? Equal meaning, different terms? Yes, the answer is in case VCR is not available and the operator wants to continue operation in gas mode, he is able to do that with the combustion stability mode. So same as we have with the ICER engines today. Another question is, good question. Is there a way so the operator can see that all cylinders are having the same compression ratio after an intervention or a change in VCR has been selected by him? Yeah, maybe.
Actually,
Go ahead, please.
Maybe I can give a comment to that. We on the control interface, control system panel, there is a specific page for VCR that can also show the individual piston positions or compression ratios. That will also be available for simple monitoring or for troubleshooting purposes.
Okay. Maybe we should clarify though that the VCR, the compression ratio is not selectable by the operator himself, but it's rather controlled by the engine control system. So the engine control system will determine what is the optimal compression ratio based on the engine load, taking into account combustion stability, maximum firing pressure. So you always operate at the highest possible efficiency. Now, another question is an estimation about the potential return on investment based on the savings that were showed. So this one,
I think we have not shown any cost figures here now, for obvious reasons, being that actually the final pricing will come from the engine builder through the shipyard. We do have some cost estimates, of course, which we discuss and review with engine builders, but they will finally then provide pricing from their side. But as we see and as we saw, the annual savings before, this would typically result in a payback of the extra cost of about approximately, say, 2 years or something like that. So fairly short payback and good investment.
Thank you, Marcel, and thank you, George. Unfortunately, we have run out of time. We do have so many more questions. So what we would do is we'll collate them and maybe we'll send out, we have a list of all your emails, so we can send out a list of the answers to the questions that we couldn't address today. Otherwise, you're welcome, like I said, to come and visit us at our stand at North Shipping and ask Marcel directly. Or you're also welcome to send either of them an email. So before we end, I'd just like to say, once this webinar is over, you'll be directed to a very, very short survey. I promise that it's super short, and it would mean so much to us if you could just quickly fill out that survey, just so that we know how we're doing and what we could do to improve in future. So we're sorry that we've had to cut this short, but like I said, we'll try and address all your questions. And thank you very much, everyone, and have a great day. Bye.
Thanks for joining, and good rest of the day.
Have a
Bye-bye.
good day. Bye.